to record. Okay. So which one?
I was just going in order on the homework questions. I got to 11 because that was one of the things.
Which section?
2.1.
2.1. Okay, so 2.1. 11. Okay.
So I see.
Yeah. Okay,
divide
this
the
one.
x
Okay,
minus
so
2x.
let's work on it.
Because I'll tell you what I was doing, and the book doesn't do it. I'm wondering why it doesn't work. So I went to the p of x and I did that e to the integral of 2 out of x, which I think is
Okay.
2
So
ln x minus 2
mu
ln x.
should be e
E to the minus 2
integral
ln x.
minus 2x dx, right? So that's
So
e.
shouldn't that go to 2x because the e and the ln cancel it out?
Oh, sure.
Shouldn't
So that becomes what? That becomes 1 over, that's what, x, 1 over x squared, right?
Why? If I do e to the integral of 2 out of x.
Well, just write it like this, e ln x, and you still have minus 2, and that's x minus 2, right?
1 second, e ln x minus.
That's that.
Minus 2 ln x. Yeah, I know that. Yeah. So
Okay. So you
when
multiply then, right?
So 1 second, the e and ln x cancel each other, right?
Yeah, e ln x produced x, yes.
So what are we left with after you take away the e ln x? Minus
Well,
2.
it's just x minus 2. X to the minus 2 power, which is 1 over x squared.
Okay.
And when you multiply and you get
you
this.
just change it. So I got mixed up with such a simple what is it called?
Yeah, you lost x
rule.
along the way.
Yeah, I got mixed up with the square rule. I got that it was x minus 2. 1 second. Why doesn't 1 second? There's something else I'm not getting. Minus 2 ln x. Why does that come x to the negative 2? Why doesn't
Well, e to the ln x is x. So it's just x minus second power. That's it.
Why is it not minus 2x? Why does it come why does it come x to the second power, not the minus 2x?
No, minus 2 is exponent. So it's e ln x to the power minus 2, right? It's the property that x to the power a to the power b
x also the exponent?
Is x a b.
But isn't the x also the exponent?
No.
ln x.
ln x. So I bring ln x together with e. That gives you x, and you still have minus 2.
Ah, okay. If you do that, okay, fine. Now I got it. That makes sense. So
and that's just this one. Okay, and when you integrate, right?
Yeah, okay, I think I know the whole thing. And then you integrate, and then someone when you multiply, what is it called? The e minus, just in general, not just in this problem, all the problems, e minus so when you get x minus 2, that's I forgot what it's called, the multiplying
that's
whatever.
multiplying
whatever that's called. So you multiply for, let's say, dy dx and the x squared cosine x, and you take the integral.
You multiply each term.
Yeah, you multiply each term, and then you take the integral. Why don't you multiply the middle term?
I did. It's now 2 over x cubed.
2 over.
It was 2 over x. If I do times 1 over x squared, it's 2 over x cubed.
2 over x cubed. So you always multiply everything?
Yes.
Even the middle term? I don't know why I'm doing the earlier problems, and it seems that we're not multiplying the.
No. You multiply each and every term.
Even though we already took that integral, we'd still do it again.
No, I mean, if you do derivative of this, it's what? 1 over x squared y prime. What's the derivative of 1 over x squared? Minus 2 over x cubed times y untouched. Product rule. If you go like backwards from here to here.
So 1 second. 1 out of x squared is a multiplying factor. You do times y prime, which just makes it y. And And then you do 1 out of x squared times minus 2y out of x. You do
Yes,
that,
that's 2 over x cubed.
and you do times and then you do times the x squared cosine x.
Yeah, it cancels out. X squared over x squared cancels out, and I'm left with just cosine,
And then you
right?
do, and then you do the integral of them all.
Yeah.
Okay. I don't know why I thought you don't multiply the middle one. I don't know why.
No, you do. You
It
do.
was working before, so I don't know.
Yeah.
Anyways,
So let's bring this here since we did it anyway. Why not? Okay, anything else?
good for now.
Okay. Well, then let's continue with 2-3. That's an important section, growth and decay. Equation is actually very simple to solve. It's just dy dx equal kx with plus sign, that's growth, and dy dx minus kx, that's sorry, not x, y. That's very important. Okay. In fact, if you create like this little diagram, if you set right-hand side equal to 0, that's only y equals 0 is solution, right? K is assumed a positive constant. So for y positive and derivative is positive, which leads to solutions going to the right. And for y negative, it's negative, so it's going to the left. But if it's a practical problem for population or something, then y is always positive. So that means growth. It just keeps going right, keeps growing. To solve it is very easy. Separation of variables, divide by y, multiply by dx. You get this, right? So it's log y equal to kx, right? And then you just plus constant, call it c1. And then you have y equal to e kx plus c1, but when you just break it apart, ec1 and ekx, just call it c2, and it's c2 ekx. So other one obviously exactly same, and you get ce minus kx, just minus, and the difference is if x is here and y is here, but you start here at 0, you get constant c, initial value, right? Y at 0 is y0. So you get that c is y0. So y1 is y0 ekx. So you start with y0, and then if it's a positive one, you go up. If it's a negative one, you decay down, okay? So k is a constant of proportionality, okay? So solving, as I said, I mean, I did it actually separation of variables, equally easy. You can do linear approach. In any case, you get this, okay? So the only thing is if you, I did it with x, it's probably more appropriate to do it with t actually, because usually it's time equation. So then your answer is in terms of time. ky, so y equal initial e case. Or if it's a decaying case, y equal initial e minus case. Okay. So you can do it as a linear approach to the multiplying factor is just e minus kt. Okay, so let's do it as well, just so that we're looked at it every way. So then you write it as dy dt equal minus ky equals 0. It's a linear equation, right? Y comes linearly. The multiplying factor e integral minus k dt, but that's just e minus kt. You multiply each term, see, second term 2. On the right, you still get 0 times 0. So this one is e minus kty derivative, right? And you still have 0. And when integrating, you get a constant C. You multiply both sides as C E K T. Okay, just like we said. So either exponential growth or exponential decay. Okay, so like we discussed here, growth or decay. And here it's sort of going right, growing, and negative, it's decay. Okay. Notice, by the way, that's sort of a side note here, this method of drawing this diagram here, one I did here. Okay. And you can draw a similar diagram in this way. It's also, if you set with 0, it's just y equals 0. For positive wise, it's negative, so it's decaying. And for negative, it's growing. But again, if you're doing like a practical problem, your y is only positive relevant. So it's growing exponentially, decaying exponentially. So what are the examples of growth and decay? There are actually a ton of them. Classical example of decay is a radioactive decay. Okay. So let's see, there is some interesting story here about finding some fossils. Some dog got lost, one of the greatest archaeological discoveries. So this remains turned out to be 15,000 years old. How they do it? By carbon dating, whereas regular carbon-12 and radioactive carbon-14, which has a specific decay rate. So when they find some fossil, they compare the decay rate in the item to like what it was when the item was alive, like was it a piece of tree or some bone. While it's alive, it's a certain balance of carbon-14 and carbon-12, and once tree dies or animal dies, that balance stops and radioactive part just decays, and they can tell the age. Okay, so let's kind of set it up. How would you think about this? So you have, would be like good to make like a little note here on what we were doing. So but so let's set it up. So chemically, it was determined that residual amount of C14 present in samples of this charcoal from Lassau's cave was 15% of the original amount at the time tree died. So there is a well-known half-life of C14. So we can use it to figure out the equation. So half-life of C14 is 5,600 years. Half-life means half of the original amount. Don't remember if I ever told this joke, where is it like a Russian joke, which element has the shortest half-life? And it's not a proper scientific question, it's just a joke. The answer is bottle of vodka, because when proper Russians open it, half of it is gone right away. Okay. So yeah, but so here it's 5,600 years. So it's also known that quantity of C14 in some charcoal satisfies this classical decay equation. So we want to find constant K using half-life. information, and then figure out the age of this finding. Okay, so let's see. It's a bit more convenient actually to derive this in general, this half-life connection to K. Let's do that. So the general dq dt equal minus kq. And we know that solution of it is q equal initial amount E minus kt. Okay, so half-life, call H half-life time. Well, half-life, but it's very meaning it's half of the original amount. So it's q0 over 2 equals to q0 E minus k times H at half-life time. Okay, so divide both sides by q0 and take log. You get log of 1/2 equal to log of E, but they undo each other and you get kh. Okay, so it's a bit more convenient to write left side as log 1 using properties minus log 2 minus kh, but notice that log 1 is 0. Log any base of 1 is 0, right? So therefore connection is that k is equal to log 2 divided by h half-life. So that's what we derived here, more like in for specific case of 5600, but it's easier to just do it once and for all for any element. Connection between k, the decay constant, and a half-life. So let's bring this here. All right, so then we have specifically here log 2 divided by 5600 years is this number, so we know now k. Okay, so the graph actually looks like this, how it's decaying. But more specifically now we know the formula. And we know that 15% of the original amount remains. So what does it mean? It means that 0.15 Q0 of original amount, whatever it was, it doesn't matter for us. They gave us percentage, that way it's convenient. So Q0 E minus KT. I didn't bother writing the constant for K. It's 0, 0, 3 zeros, and 1, 1, 2, 3, 7, 8. 1, 2, 3, 7. Whatever it is. Okay. So you, and we want to find now the time at 2, right? So you divide again by Q0, take log, you get log 0.15 equals to minus KT. So the time it took is log 15.15. Divided by K. So that's log of 0.15. Well, negative, really, minus K. So, and you have here minus this number, 0.8. Oh, come on, what's going on? Zero point zero 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 1, 2, 3, 7, 8. 1, 2, 3, 7, 8. Okay. So log ln really, ln of 0.15 over minus 0, 0, 0, 0, 1, 2, 3, 7, 8. And that's about 15,000 years. Okay. So that's that. Okay. So let's bring this as a picture. Okay. Any questions? And that's a general relationship. Log 2 divided by half-life gives you K. And for most standard radioactive materials, half-life is well known. So you can use it. Okay. So that was radioactive. Yeah, question?
A quick question. Does that hold for like a third life, for example? Would LN3 be the third life?
I suppose, but half-life is a standard. I haven't heard of measures of other. Half-life is a standard, yeah.
Okay.
Okay, so that was radioactive decay, which is example of decay in exponential behavior. And here's a great example of increasing exponential behavior, compound interest, okay? So that's a grow future value in the savings account. So if you deposit a sum of money as 0 in a bank account, and there is interest depending on the amount in the deposit, that's compounded kind of account, then you get this exact kind of dependence, okay? So that way you can get future value depending on a rate of interest the bank pays and frequency at which you get this interest payment. So there are two kinds, discrete kind of payments and continuous, and you've probably seen this in calculus or some other course, but it's such an important thing that it's definitely worth repeating. And we're going to derive everything here. Yeah. There is actually interesting continuation to annuities. Yeah, there's all kinds of, this is a longer section a bit. There are all kinds of interesting things, and like there is 28 has to be done in class. Some other stuff better be done in class. Actually, there are some more interesting problems here. Bombarding plutonium, elimination of drug in a system. There's all kinds of interesting stuff here. But 28 has to be done in all detail. That's usually, this logistic growth model is usually like a whole section in other textbooks, but he chose to put it into the homework. So, but I really want to show it in all detail. Yeah, there's all kinds of interesting things here. It's a big section, big homework especially. But we'll try to work on it, and there is the mixing phenomenon. Yeah, mixing is also interesting, although a bit tedious, kind of mixing phenomenon. Of cooling. Yeah, it's all kinds of great stuff here. Direction, field, high order. So it'll probably makes sense to have midterm after chapter 2. And then 3 will go to final and whatever we can complete here. I mean, there's all kinds of interesting stuff here, but there's not enough time. Okay, so let's see. So first compound interest, which is discrete. Let's work that one out. So if you have, say, initial deposit as 0, what happens after 1 year? Well, after 1 year, assume for now it's just once a year compound. It's just, well, what it was times R times the interest. So you get 1 plus R, well, as 0, really, 1 plus R. Then what happens next year? Well, it's what it was already as 0, 1 plus R. And interest is compounded on that amount. That's the idea of compound interest. So it's R multiplied by already another 0, but it's 0, 1 plus R. Well, if I factor as 0, 1 plus R, I get another 1 plus R factor. So you have a 0, and you have 1 plus R squared. And you can get the idea. This is after 1, this is initial, then you have initial. After 1 year, after 2 years, you have a square here, and you guess the general formula. After t years, st is S0, 1 plus r to the power t, right? But what if you compound not once a year, but twice a year, or generally n times a year? You get this formula. So it's for, you get for each one s of t S0. The multiplication factor is not 1 plus r, but 1 over r over n, by same idea. But how many compoundings? Not t, but n times t, right? So that's the formula for discrete compoundings n times per year, okay? So it could be twice a year, semi-annual, quarterly, 4 times a year, monthly, 12 times a year, daily, even consider it 365 times per year, etc. Okay, so here they took such an amazing annual interest rate of 10%. Who can get 10% ever? Okay, so 10% interest, and you see that compounding, more often you compound, see, annual, semi-annual, quarterly, monthly, more often you compound, it grows a bit faster, not huge difference, but a bit faster. So more often you get the compounding, naturally, slightly bigger amount of money you get, okay? So that's good. Now, there is a very interesting limit here. What if you keep compounding more and more often, okay? So there is a limit of n going to infinity of this formula. So let's work this out, okay? So there is a trick actually oftentimes used to do this. You call, let's see, let m be equal to n over r. And r is a fixed rate of compounding. So if n goes to infinity, m will go to infinity as well, right? But m is equal to, n then is equal to m times r. So we can rewrite then our expression here as limit as m goes to infinity. Initial is 0. Now r over n is flipped n over r, so it's 1 over m. Then I have n is m times r, right? So I'm going to write like this, m and then to the power rt, okay? But what's the limit as m goes to infinity? 1 plus 1 over m over m. Anyone knows? From calculus, guys?
E.
E, exactly. We can prove this directly with either numerically or with L'Hopital's rule. But let's just use the fact, and it's S0 ERT. So that's called the limit of continuous compounding. You compound more and more often. In the end, you compound really continuous. Okay. So notice that this was not really differential equations doing this, right? This was so-called difference equations, if you'd be more precise, but really we just followed logically the step. While after taking the limit, you get kind of a continuous solution, continuous compound. So if you have this initial value problem, you get a 0 ERT. We proved it here by taking the limit of discrete compoundings, and it looks like this. But you can actually solve a differential equation. And in fact, when you do solve a differential equation, it pays to generalize it a bit more. So what if not only you put some initial amount to grow in the bank, but what if it's annuity? When you're adding, let's assume adding continuous. I mean, in reality, of course, you add discretely. You don't bring like a few cents every day to the bank. You do it like once per month. But for simplicity, let's say it's broken into the D rate for continuous D rate. Okay, so then what you are solving is this equation, ds dt equal to rs plus d. That's annuity. Okay. And this is a linear equation. And here I've gone through the details of solving it. So what should we do? We bring rs to the left. Then it's a linear equation with p equal minus r. So you have e minus r dt. So you multiply by e minus rt each and every term. This then is e minus rt s prime, right? And you have this. Now you integrate. Left side is just undoing derivative, but right side you have to integrate e minus rt over minus r. And if you multiply now by e positive rt to get to s, you get with CRT, with exponential growth, and minus d over r. And if you have initial condition, initial amount, you put into bank as 0. So if you plug 0 here, you get c minus d over r. So you have a 0 plus dr. So you get this formula, okay? In fact, we wrote it this way, by the way. I think for problems, if I remember correctly, for many problems, it was actually advantageous not to separate these two terms. See, we separated as 0 ERT and d over r. We did ERT minus 1. So for many problems, it's better not to separate and keep it also in the other form. Let's do both. So let me keep this. Let's also write it intermediate step we got between here. Let's say that it's S0 plus d over r, ERT, and minus d over r. That was useful too, if I remember right. Let's keep this here as well. So let's apply it. And there are some interesting problems practical, like what if you stop smoking, if you God forbid smoking, that's a dangerous habit for your lungs. But what if you quit smoking and just, so Jenna entered college, quit smoking. She smokes pack a day, 2 packs a day. Oh, that's not good. Which translates into about $30 per week. Suppose she makes a weekly deposit of this $30 instead to the bank. And bank pays unbelievable rate of 10%. Good luck finding that. But let's say compounded continues. So when she retires in 47 years, how much money that will give her, okay? So what do we know? So Jenna's weekly deposit 30. And so let's do it per year. So we do annual, 30, 52 weeks, that's 1560. Okay. So we basically have here what? We have R is 0.10, unbelievable 10%. D per year 1560. We do it in terms of T is going to be therefore measured in years. T years. That's why this is computed for the entire year. D. And according to the solution we got, or one of its forms at least, let's bring both of these forms here. So let's see, what says 0 in this case? Initial amount, well, nothing. She just starts, she doesn't deposit any money in advance, like in time 0, she just keeps getting this $30. So according to say this solution, S equal S0 ERT plus T over R ERT minus 1. So this is 0 because S0 is 0. And D is what we said 1560 and R is 0.1. So it's 1560 an extra 0. And ERT 0.10 T minus 1. So that's the solution. And after 47 years, you just plug T equal 47. She's gonna be a millionaire. Almost 70 or almost 1,700,000. That's of course very idealized, you know. That's really like 10% growth rate. We're gonna get that, you know. More realistically these days, like at best you're gonna get 2%. Let's compute it for 2%. So that would be 1560 over 0.02 E 0.02 times T47 minus 1. Let's compute that. That's more realistic. So 1560 divided by 0.2 question. Someone has a question?
How did you get it?
After let's compute it at $10 a pack, because they're computing it at $2 a pack.
Sorry?
They're using $2 a pack.
Oh, right. Yeah, so she's saving more, you're saying.
Yeah,
That's true, yeah. Well, let's just finish this calculation and then change that as well. So that's second ln to get to E 0.02 times 47 close parenthesis for E minus 1 and close parenthesis there. Well, it's not millions, but still some money, you know. And if it goes not at $2 a pack, but $5 a pack, you'd have to multiply this by 5, right? So that's already like over 600,000. So not only it saves you a fortune not to smoke, but I mean, most importantly, of course, you don't die most horribly young or not so old from it. That's the most important. But it's in addition, it saves you a lot of money. Okay. There is also like a fun calculation I remember doing with students. So everybody remembers that Indians sold Manhattan for $24, right? It was around 1600. So if you say, assume like yearly compounding of say 5%, so $24 times 1 plus R let's say 0.05. And it's been like about 400 years since then, right? So to the power of 400. So that's what, if you could put it to the bank consistently for the 5%, that is about 7 billion. Which is a lot, but I don't think it covers the cost of Manhattan, right? All the buildings and everything cost more than 7 billion, I suppose, right? On the other hand, what's interesting, that if you let it grow, say not at 5%, but say at 7%, then it's already e to the 13. And e to the 13 is what? It's trillion already, right? And with trillion, you can probably claim that you can buy the whole Manhattan for like 1.3 trillion.
I have a number online, 825 billion. What can we calculate what rate we would have to grow in order to get 825 billion?
Let's see, we should be able to. So that's an equation like this. So we have equation future value, initial value. So I did discrete compounding here, 1 plus R to the power T years, right? So now we want to know how many T years. That requires logs, right? So it's S over S0 1 plus RT. So how do you get to T? It's a ln S over S0. Okay. And you have T ln 1 plus R. So T then is log of a ratio of amount divided by the log. Oh, wait, we need rate. Sorry. We're solving for rate, not for time. Time we know. But to get to rate, we don't need logs, right? To get to rate, we need just roots. 1 plus R is equal to S over S0 to the power of 1 over T. And R is this, right? So you said how many? About 800 billions, right? So 800 billion. So it's 800, another 30, right? So this millions, and this is a billion, and this is 800 billions. Okay, so let's see, we want to insert ln of that divided by 24. Okay, and divide by, oh wait, I'm tired today. I'm still doing lns. You have to do this. So parenthesis 800 billion is what? Billion is 10 to the 9. So another 2 zeros, it's 11. So 8 times 10 to the power 11 over 24 to the power 1 over 400 years approximately, and minus 1. So that requires about 6.2%, which is not unreasonable rate, right? I mean, it's a large rate by today's measurement, when the best you can get 2. But if you think about like many years on average, it's not entirely unreasonable rate. So that's interesting. Okay, so let's do 28 in detail. That's like a big, interesting new thing. Yeah. So that's classical so-called logistic model. Came originally from Verhulst, logistic growth model. It looks like this equation. Let's actually bring this. Well, okay, so let's just. Okay, so you have dn dt equal to Rn 1 minus n over k. Okay, so before we do analytical solution here, it's really good idea to do this kind of qualitative solution. So how you do qualitative? You set the right hand side to 0 and solve it, and that's just n equals 0 and n equal k, right? So then you mark this on a line, and you try to figure out the signs of the right-hand side, and these are also signs of the derivative. So if n is really large, what happens then? Well, this is r is positive, n is positive, but for really large n, this term will be negative n more than k. So negative whole thing, and negative means you have here minus, and therefore solutions are going this way, we're decreasing, negative derivative. Then between 0 and k, like k over 2, positive, 1 minus half positive, so you have plus, and therefore it's going right, okay? And for negative ones, although this is not practical for population, say, but let's do it as well. So if n is negative and this is negative, positive, negative, and this one, 1 minus negative, positive. So that's negative again. So it's decaying solutions, negative derivative. So if you draw like approximately looking solution already, we can do this by marking, say, time and marking n here, and you have k and you have 0. And so what it tells us that if it's negative, you start with negative initial condition, then it's going like to negative. It's decreasing. So those just go like this. You start between 0 and k by increasing. So increasing, but it has to taper off to not cross this. It cannot cross such so-called. Well, we should say a couple of things how this method works, but this is so-called stationary solutions. Book does it, but a bit later, but I think it's important to talk about this right away. Stationary solutions. So it cannot like cross it, it's another solution, but it just kind of approaches it. And if you start with n above k, then it's supposed to decay negative derivatives. That's here, right? Negative derivatives. So it's supposed to go down in this method. So what it implies is that this k is so-called stable solution, n equal k solutions approach it nearby. This one is unstable. You can kind of see to stable ones where arrows point to, so solutions approach this. Conversely, from unstable, they go away. Okay, so stable, unstable. Okay.
It sort of makes sense because then you're estimating a negative population size.
Well, negative population doesn't make sense, but it's good to at least kind of draw this as well, at least from math point of view. So that also explains by the way, so R is this growth rate, and K is so-called carrying capacity. See, if you start below carrying capacity of population, your population increases. Start above carrying capacity of population decreases. This is much more realistic than unbounded exponential growth, because most populations have limited resources, so they cannot grow at infinity. I mean, human population is much more complicated. It doesn't, you cannot describe it by simple logistic equation. But like say, if you have bacteria in a dish is limited. And however quickly bacteria grows, it still follows this kind of law. It may grow initially very fast and then it tapers off. Okay. And say if we're talking about, say, I don't know, foxes in a forest or wolves in a forest, like if population of wolves becomes too big, not enough rabbits to support them, it starts to decline. Right? And if it's below carrying capacity, wolves are still multiplying. So that's a very good model. Okay, now, so that's good, but that's qualitative solution. Let's get the actual formula, quantitative solution. Okay, so again, I want to do it in general, and that's well explained here. Let's look step by step. So first of all, this what type of equation it is. It's not linear, there is n squared here if you multiply, but it's separable at least. So I can bring n and 1 minus n over k to here and have all n's here, and r dt will be on the right side. How to integrate this though? Well, not obvious, but it's calc 2 kind of expression which you can do partial fractions for. So I call this a over n and b over 1 minus n over k. And a and b I have to find. Well, it's usual formulas for doing the partial fractions, right? So I write 1 on this side, a times 1 minus n over k, and b times n. And if you set n equals 0, then this is gone, and you get a equal to 1. And if you set n equal to k, so that this one is gone for n equal k, your b is equal to 1 over k. So you get this expression. And good news is that this you can integrate. So you get log And this is negative here, so you get minus, and you have log 1 minus n over k. Think about it. If you differentiate this, you get 1 over 1 minus n over k. And by the chain rule, you get extra minus 1 over k. So minus cancels, and you exactly get this 1 over k. An integral on the right is just RT plus log. And then you bring this together, n over 1 minus n over k and log, and apply exponent. And that gives you this. So if you put here initial condition and 0 initial population, you get this equation. We kind of continue it here. So what happens then? So you have this initial condition. Now there is a little bit of algebra. I called this whole thing psi, Greek letter, and I cross multiply it to solve for n. Then you get this messy expression, but if you bring it to common denominator via multiplying one top and bottom by 1 minus n0 over k, you get this, and if you multiply by k top and bottom, finally, you get final solution. So the final solution is n0k and 0 plus k minus n0 and e minus rt. So that's the analytical solution. So again, it's much better to do it once and for all, rather than, redo it each and every time. What's this? I think that's just another problem, this cat and mouse problem. Okay, let's just finish working with this. So we got qualitative, we got analytical. One thing very important to note about this qualitative solution here is that you can only do this kind of qualitative approach because here on the right-hand side, you don't have time, right? Then it makes sense to set it to 0. You get fixed, indeed, stationary numbers for n and k, where the right-hand side equals 0, and picture is kind of stationary in a way. I mean, it's differential equation changing in time, but the picture is stationary. If I had time here explicitly on the right-hand side, I wouldn't be able to do this. So equations which don't have time on the right-hand side have a special name. This is so-called autonomous equations. Only for them you can apply this qualitative methods. These qualitative methods are good because they are really like allowing you, here we can do analytical solution, but so many times you cannot do analytical solution, but you can still do the qualitative, and that really helps. Okay. So anyway, so let's do some numbers. So what I got in general is that n is equal initial n0 times carrying capacity k. And I have n0 plus k minus n0. K minus n0, e minus rt. Okay. So that's general solution. Now, what do we want? What do we know? R is 0.03, K is 200 million, and 0.4. So let's try to plug in and see what happens. So 4 times 200, 4 plus K again 200 minus 4. Okay. And E minus RT, but R is 0.03T. So that seems to suggest that we have 800 over 4 plus 196 E minus 0.03T. Okay, so let's see. Okay. Use separation of, okay. So if you plot, so plot is like this. See, starting and going like that or decaying exponentially. So this plot, by the way, where do you get this plot? This plot you get here direction field plotter. 921 to get here. Okay, so it's y and t. So okay, so you have r 0.03 times n times your y unknown times parenthesis 1 minus y divided by r, which is 200. Okay, so if I graph direction field, it doesn't look right because I don't have a good bounds. So I want to go from 0 to maybe like 20, and from let's say 0 to 300 and what? Something not good. Hold on. Page and responsive. Okay. Come on. Wait, the whole internet went down. Can you hear me, guys?
Yes.
We can hear you.
Yeah, and I mean, I can open email. I guess it's just that web page. But anyway, this is what you're supposed to see. Okay. Okay, so that's that. Evaluate N200 with a estimate for population in 1990. The actual population was 250 million. Well, you just plug in, right? So that's N200. So 800. Let's actually check it in. Where's my solution menu? Here. So this would be 2, 3, right? 2, 3, 28. Right, so let's plug in. So 800 over parenthesis 4 plus 196 times exponent minus, well, you have to be careful. You have to use this minus when you need to enter negative minus 0.03 times 200 years. Okay. Yep, you get 178. Okay. So the actual population of US 250 million, quite a bit more. But again, it's for human population, it's not terribly good model. Because we're just kind of,
But he estimated the carrying capacity at 200, so it always
yeah, so it
200
has
million.
to stay below 200.
Yeah.
So as I said, it's not very good idea to use it, you know. Okay, so let's bring this as a picture as well. Okay. Any questions? Okay, so let's just take a break, come back and work some more. Okay.
Oh yeah, quick question, Professor.
Uh-huh.
Do you know when you would have the recording for the second lecture?
I hope let's try to have it all up today. Email me if you don't see it by the late evening. Okay.
Okay. See you in a couple months.
Zoom. There. Okay. So there are actually many interesting problems here in addition to what we did. All kinds. Yeah, I wrote some up. Decay in biology, blood alcohol level. So let's maybe look at this one just to have. So in many states, illegal to drive a blood alcohol level more than 0.10, 1 part of alcohol per 1,000 part of blood. Someone who was involved in that auto accident was 0.20. Assume that percentage of alcohol in bloodstream decreases exponentially at 10% per hour. So what's percentage in the bloodstream anytime and how long before can legally drive? So first of all, it's exponential decay. So y0 e minus rt. Okay. So what do we know? We know that percentage of alcohol decreases exponentially at rates 10% per hour. So that means that after 1 hour, you have 0.9 of original amount minus r times 1. So that will let us find r. So y0 cancels, log 0.9 minus r. So r is equal to negative log 0.9. And that is 0.105. Found it here. And then we want to, so initial amount we were told 0.2. That's how much he drank to 20%, 0.2. And with decaying. And we want to know when it's gonna drop down to 0.1. So what time? So we solve this exponential equation. It takes almost over 6.5 hours, 6 hours to get to safe level. So if you drink a lot, don't drive for the next like 6-7 hours. Okay, it doesn't dissipate that fast, at least with 10% per hour kind of rate. Okay. So there are lots of interesting problems here actually. Have to do some other stuff, but there's a lot of good stuff. Okay, any questions? So try to do the homework. Okay, so let's look at the next section. So that's somewhat tedious section, actually, mixing phenomena. So, that's one of the applications of the linear equation. Okay, so we consider mixing problems. So substances mixed in chemistry and biology. And it's not just like actual mixing of substances in chemical situation. It could be hormones and biological situation, etc. But let's consider like a container here where fluid is mixed. And there is a flow in and flow out, okay? In the most basic sense, if Q is the amount of substance we're interested in and the solution, like say amount of salt in a solution, then dq dt, the change of it should be rate of salt coming in minus rate of salt coming out in most general sense, in and out, whereas a tube in and tube out. So this has to be then written in more detail, okay? So rate in is what? It's a concentration in, say, pounds per gallon if you measure. So if you do pounds per minute here, rate in. It's a concentration coming in pounds per gallon and flow rate in, gallon per minute. And similarly out, again, concentration out, pounds per gallon, and flow rate out, gallons per minute, okay? And you basically just write it out in a kind of particular situation and see what happens, okay? So let's look at the standard mixing problem. So you have a tank with 50 gallons of pure water, and salt solution with 2 pounds of salt per gallon of water is poured into the tank at 3 gallons per minute. When the mixture is assumed well stirred and it drained out at the same rate. So what's the equation? And we can answer all kinds of interesting questions. Okay, so the right dq dt. So rate in 2 pounds, so 2 pounds per gallon of salt at the rate 3 gallons per minute. See, gallons will cancel out and you have pounds per minute. Rate, pounds per minute, makes sense. So out rate is what? Well, what is the concentration of coming out? Well, we don't know. It's Q, whatever it is at the moment, out of the total 50 gallons. So that's again labels per gallon, multiplied by the rate out. And that again is 3 gallons, because in and out rate same, 3 gallons per minute. So you get then this equation, dq dt equal to 6 minus 3 out of 50 times q. And initially there is no salt. Q of 0 is 0, okay? And well, that's a linear equation. So mathematically, it's an illustration of the linear equation problem, like this. Okay. So we can solve this, right? So that's a multiplying factor is mu e integral of 3 over 50 dt. Well, that's just this 3 over 50 t. You multiply each one. Oops. Six. Okay. So d dt then q. So equal to 6 times e 3 over 50 c. So you integrate 6 and you have e 3 over 50 t over 3 over 50 and plus a constant, right? And so 6 and 3 cancel, right? You get 2 and over 50 comes up, so that's 100. So you get basically then q equal to c e, well, this is t here, 3 over 50 t with minus and plus 100, right? Okay. And then we have to figure out initial conditions. So q at times 0 is c plus 100, but there was initially no salt, so c is negative 100. So you can rewrite then q as 100 comes out, factors out 1, and minus near this exponential term. So minus e minus 3 over 50t. Okay. So then at time 0, you start at 0, 1 minus 1. And when it grows exponentially and in a limit of t going to infinity, it's exponent with negative, right? Negative exponent. So that goes to 0 and you get 100. So that approach is 100. Okay. So there is actually limiting amount here. In fact, this type of equation, dq dt equals to, what was 6 minus, 3 over 50q. We could have figured out behavior, not analytically, but qualitatively, right? So you set this to 0, right? So it's q equal 100. So for big Q, it's negative, so it's going to here. And for like 50 or something, it's positive. So it's like this. So it's a stable point where solutions converge to. So like this, like that. Okay. Any questions? If you put like 120 hours, it gets already pretty close to 199.92 pounds. That's like going to max possible. Okay. Any questions? All good. So that was the case where you have equal amount coming in and coming out. If it's not equal, so unequal rate of input and output, then it gets a little bit more involved. Not much more complicated, still a linear equation, but a bit more to think about. So often flow rate of a liquid entering the tank is not the same as the one leaving the tank. And say tank either fills completely or empties. So let's say look at the case where you have flow rate is less than the output. Okay. So rate in is less than rate out. So it's going to empty over time the tank. Okay. So some type of here. Yeah, so have to figure out. Okay, so let's work out the details. So you have tank initially has 100 gallons of water, of which 10 pounds of salt initially are dissolved. So salt solution at 0.5 pounds per gallon of salt is poured in and poured out. The mixing is mixed water poured out at 1 gallon per minute. Oh, wait. At a rate of 1.5 pounds per gallon, at rate 1 gallon per minute in. Mixture is stirred and drained off at 2 gallons per minute. So find initial value problem, etc. Okay, so let's work this out. So dq dt is rate in. Well, we have 1/2 pounds per gallon times 1 gallon per minute rate of flow in. Minus, now the stirred amount, what's the concentration in the mixed amount? It's Q over how much water you got, but how much water you got? We know that of a whole tank initially contains 100 gallons, okay? So there is 100, and then there is a flow in at 1 gallon per minute, but when there is a flow out at 2 gallons per minute, So it's like this, 1 minus 2t. Whereas 100 minus t. By the way, if you set this to 0, at time 100, it's going to be empty completely. That's important to keep in mind. But that's how much water you have at, like the whole liquid you have at any particular time, 100 minus t. So you're not dividing by constant anymore. Rather, you are dividing by the 100 minus t in time. So this is in gallons, in pounds per gallon. And the rate is 2 gallons per minute. So that gallons cancel out and you have pounds per minute. So your equation then is still linear, but a bit more complicated. So it's dq dt plus 2q over 100 minus t equals to 1/2. And t only makes sense, like we said, between 0 and 100. It drains out then. And initial amount of salt we were told was 10 pounds. So that's the ODE, meaning the initial value problem, right? Not just ODE, but also initial condition. IVP, initial value problem, we're trying to solve here. So it's still linear, we still apply the method. So multiplier, integrating multiplier e 200 minus t, oops, integral dt. So it's minus t, so it's minus 2 log 100 minus t, right? Because then if you do derivative of this, it's minus 200 minus t. And extra minus 1 from the chain rule would kill this minus, and you get this expression. So this again involves E and ln. So I'm going to combine ELN, ALN here to undo each other, and I still have minus 2. So it's 1 over 100 minus t squared. So that's the integrating factor. Okay. So you multiply, this is a typo. See, it's 100 minus t squared here, not here. See, this was a typo. So we multiply. So it's 1 over 100 minus t squared dq dt plus 200 minus t cubed, right? Because it was 100 minus t already. Q1 equal to 1/2 100 minus t squared. Okay. So the left side is supposed to be full derivative of this expression. Well, the right-hand side is what it is, whatever we found before. Right? Any questions? Nope. Okay, so now you have 100 minus t squared here integrating. So it's integrating minus 2 power. So it's minus 2 plus 1 minus 1 and divided by minus 1, meaning it's this, right? So it's that to the first power, but there's extra minus 1 because it's minus t, right? So this minus 1 will cancel that minus 1. You have this plus a constant. So we're just multiplying then. So it's a bit tedious. So it's c 100 minus t squared plus 1/2 minus t, right? Yes. So now we know that the initial condition is 10. So q at 0 is c 100 squared plus 50, and that's equal to 10. Okay. So that means c is what? Minus 40 over 10,000. Yeah, minus 40 over 10,000. So that is minus 1 over 250. Right? Let's see. 10,000 over 40. Yeah, that's 250. Okay. So that's what happened here. Okay, so that means you got q equal to 1/2 minus t minus 1 over 250 100 minus t squared. Okay, so that we propose to actually rewrite like this: 250 1 minus 250. So you have 100 minus t factoring out. And what do you have then? You have 100 minus t and 250, 125, right? So minus 125 here. So, right, so that is 1 over 250, 100 minus t. I mean, you could keep it this way, really, too. Nothing wrong with that, although you can get some interesting insight here when you factor. So 100 minus t, then you have minus 25 minus t, but if you flip sign here, you have -1 minus over 250, t minus 100 and t plus 25. You set it to 0, by the way. You see that as it should be, it's equal 0 at t equal 100. It's also equal 0 at t equal minus 25, but that's not physical, right? It's t is time. So you cannot set time negative here. But at time 100, when it drains out completely, concentration is also 0, right? So that makes sense, okay? And one other thing important to note here is that what we found is Q, and Q is the actual amount labels of salt, right? On the other hand, we also wanted us to find the concentration. So B was the actual amount of salt. Concentration C is not the same, okay? So concentration is the amount of salt divided by how much total. So C is Q over how much liquid, and that's 100 minus T as we know. When you divide, T minus 100 will cancel here with extra minus, and you see that it's T plus 25 over 250. So we see, interestingly, that concentration is actually a linear function of time. and it starts at 110, 25 over 250, and when it grows linearly, and we know at time equal 100, the whole thing is gone. And at time 100, C at 100, 125 over 250 is 1/2. So the highest concentration is reached at when it kind of dries up the water. You just have a salt kind of, and that's 1/2. Okay. So that looks like this. There is a parabola here for the concentration of actual salt, which is maximized around here, and 0 here. That's actual amount of salt, but concentration reaches max at the biggest time. Okay. Any questions? No. So there is a bunch of problems here. Standard tank, rate in, greater than rate out. Actually wrote out with details here. There is cascading tanks. That's kind of interesting here. 2 tanks. In general, one gets a bit tedious, but like just a few is okay. So I looked at this one. What's that? Drug oh, that's interesting. There is a drug metabolism for problem. The rate at which drug is absorbed into bloodstream is governed by this first order linear equation, C of t. And when we can solve it, if there is initially no drug, you get this dependence. There's some interesting things you can do here. So that's that. Now, Newton's law of cooling, is it a new section or it's a continuation of this section? Wait, confused. Is it another section already? Cooling and, yeah, that's already at section 2.5, cooling and heating. Right. Yeah, starts here, just missed the beginning. We have a bit of time, not much, like maybe 10 minutes at most. So let's see. We have interpretation of time constant. Yeah. 13 to 15 should be done in class. Yeah, those are a bit more complicated with changing environment. Mechanics, yeah, there's all kinds of interesting stuff. Let's maybe start a little bit talking about cooling and heating phenomena. So the Newton law of cooling, basically the idea is that you bring like a hot cup of coffee into the room, and of course it cools down. Or if you bring like really cold water, like a cold drink into the room, it heats up in a limit to the room temperature, okay? So say steel ball is placed in pan of boiling water. So the ball is heated to 212. Assume heat flows so fast through the ball, the temperature same at all points of the ball. So we now take the ball for water and place it in a room at 70 Fahrenheit. So and after 10 minutes, the temperature of a ball is 150. How can we find temperature of a ball at any time? Notice that unlike just exponential decay in the radioactive material, that's radioactive materials are standardized. This is just some ball, or like you talk about heating something in the oven, you know, that's not like some standard materials. You have to do like an extra measurement to get the rate of decay, say, of temperature, or increase of temperature in the oven. So this requires some extra measurement. Okay. So let's see. So in general, the Newton law of cooling says that the rate of change of temperature is proportional to the difference between the temperature and the surrounding medium temperature M. And notice qualitative approach here, it's good to do. If you set this right-hand side to 0, the stationary solution is T equal M, just the medium, and it makes perfect sense. If you bring something at the medium temperature, guess what? Nothing's gonna happen, right? The temperature is gonna stay at the medium value. Okay. So you have then M here. Well, you can put 0 just because to put like 0 temperature here. Although really I shouldn't probably put 0, it sort of confuses me. It's just T equal M, that's it. So, and if T is greater than M, then this term is positive, but there is minus K negative. So there is minus here. So temperature converges to M from higher values, but it also converges to M from the lower values as well. Because for T less than M, this is negative, negative, positive, plus. So solutions kind of look like this. You start here, you go there, and if you start here, you go there as well. Okay. Should be said though, it's not like I did not draw this well. It's sort of more just like this, just pure exponential growth. So that's a qualitative approach, right? Qualitative. And quantitative, it's, I would say, what's easy? It's separation of variables, or it's linear, really. Probably linear, you see exponents a bit better. Let's do linear. So you write dt plus kt and equal to km, right? So if you expand this, it's minus kt plus km, but if I bring kt on the left, it comes with plus. So the multiplying factor, just integral of constant k, so it's ekt. So you have ekt derivative plus k, ekt, and you have km ekt. So the left side is derivative of ekt times t km ekt. Okay. So integrating, left side we're just undoing the derivative, and right side it's like a chain rule in reverse. You get extra k here, canceling this k. So you have an ekt temperature m ekt, well, plus c, and then we divide by ekt. Okay, so let's actually let's put plus c right away here. So t then is c e minus kt plus m. And if you just get the initial condition, t of 0 is c plus m equal to initial temperature T0. So then T is T0 minus M E minus KT plus M. That, by the way, should convince us right away that, come on. So that converges to M as t going to infinity as it should be from the graph, right? Yeah, actually, I did separation of variable integral, both methods I did. So that goes to M as t goes to infinity. And you have your solution. And I actually prefer to write it this way rather than combining. The book seems to rather like combining M terms together. I think it's better to keep it this way for solution's sake. That's what you get. So let's maybe do at least like one problem. We call it a day. So you have at 12 midnight temperature in mathematical building 70 Fahrenheit and outside temperature 20 Fahrenheit. So like cold winter, but furnace breaks down. 2 hours later, temperature already 50. That's terrible. So find initial, so what's initial value problem, etc. So assume outside temperature remains 20. So you have then t equals to t0. Initially it was 70. Surrounding 20, e minus kt plus surrounding 20. Okay, so that's 50 e minus kt plus 20. Now what's k? We don't know, but we know that 2 hours later it's 50. So 50 equals to 50 e minus k times 2 plus 20. So you have 30, 50 minus 2k. So divide by 50. You get 3/5 equal to e minus 2k. Apply logs, all right? Oops. So k is minus 1/2 log 3/5. So that comes to 0.255. And when we have our model done, it's 50 e minus 0.255 t plus 20. And you can answer any question. So what questions do we have? Temperature of a building or remaining of a night is this. So determine the temperature will fall to 40 degrees. So really like bad. So if we set this equal to 40, 255 t, 50, and 40 minus 20 is 20. So we get one after dividing 2/5 and taking log minus 0.255 t log 2/5. So solving for t, this gets us only about like 3 hours, 3:59 hours or 3:56 minutes. That's not long. So the building is really gonna get cold very soon without heating. Okay. Any questions? No? Let's call it a day, guys.